I would like to start with wishing you all the best in New Year. And talking about the New Year, we should remember about the end of semester approaching fast, very fast now. And well, as you know, we will start students' presentation next week. And please reserve terms, because situation for today looks like this. There is a portal page devoted to information technologies. And first lectures, as you can see here on dates, are given previous year, but starting from the lecture 7 probably. These all are new recordings, so you can got them here. Here will be the last recording, not exactly the last, because I will try to record also your presentation if you allow me for this. And we have still 2 slots for next week. Three slots. For this week, and no free slots for the last week. I don't know exactly how many people, some of you like in here, don't tell me how many people will take part. I can see that Mr. Korzeniowski put here only one, so probably it's his individual presentation. I will have to adjust number of presentation that can be given during each week. Probably I will send you an email asking how many people is involved in your presentation this week. So after this, I make the decision allowing to all make presentations. Sometimes there will be not much time, unfortunately. 90 minutes for presentation gives us about 20 minutes per presentation. Lowering this time to 10, 15 allows to give you a little bit more presentations. Do you have any questions to this? If no, please make reservation, and I will try to solve some problems this week. If there are no questions, I can start today's lecture devoted to efficiency of algorithms. And well, let's start from some short introduction. thinking about something quite different than making software. Let's think about building a bridge. When asked to construct the bridge over a river, well, it's quite easy to prepare some construction, some plan, but quite often the bridge can be built in incorrect way. For example, it's too short, doesn't reach the other side of the other bank of the river. It's not strong enough to carry all the traffic, especially during the rush hours. Sometimes it can be not wide enough for the required lanes. So, well, there's, you know, an expected lowering the width of the lanes and problems. But even if the construction is okay, sometimes it will need too much manpower, too many materials, too many components, or too much time to bring to completion. This means that the proposed construction is too expensive. And making development of any other real construction, these are the main problems. The construction must not only fulfill the requirements, but also have to fulfill some other requirements connecting mainly with time and money. The same is with software. It's very easy to construct, to build bad algorithms, but very often good algorithms who can solve the problem and give a solution are not usable because the solution can be easily, they can give solution easily in cases when there's a small set of test data, but doesn't work well with real data. So I will try to tell you something about these algorithms. Let's start with something very simple. This is Fibonacci series. As you know, to count nth element of the series, you have to add previous two elements, and exist two kinds of algorithms. The first one is recursive, like this one written on the slide, and the second one is non-recursive. And look here for execution times, and I will try to show that these numbers are not taken from the air, from the ceiling or whatever. Oh, doesn't work. Why? I don't check this. Well, still doesn't work. I probably have to tell how much. No, sorry, really sorry, doesn't work. The prepared software doesn't work at all. I was happy that I have found this code. Well, look at this. Why the recursive version is so slow? I tried to told you about this on one of the previous lectures, but well, to compute the compute nth element of Fibonacci series, we will need these elements. So let's see how to compute the fifth element for short. On one side, I will have Fibonacci of 4 and Fibonacci of 3. To compute Fibonacci of 4, I will need Fibonacci of 3 plus Fibonacci of 2. And once again here, Fibonacci of 2 plus Fibonacci of 1. As you can see, in this simple case, to compute one value of fifth value, I will compute once this, twice this, 3 times this, because Fibonacci of 3 is Fibonacci of 2 plus Fibonacci of 1. So, as you can see, 1, 2, 3. When the value rises, the value of n rises, we are computing every term of Fibonacci series more than 2 times. So times grows that way. At the beginning, the algorithm is very fast. Next, as you can see, for n equal to 45, we have to wait 13 seconds to get answer. But when programmed in non-recursive way, everything works better. The time doesn't depend on n, because you have to store only 2 previous values to compute the third one. And at next step, you can forget the oldest value, still keeping in memory only 3 values. Operations are very simple, addition. So, as you can see, both got the same result, correct result, but in first case, the time is too big. Well, if the n is not very big, there's no problem. You cannot distinguish between 3 milliseconds. This is time in seconds. So here you have 3 milliseconds and 1.2 seconds. The difference is undistinguishable. But here, the difference between 1 and 14 seconds is really very big. And the same can happen also with memory requirements of an algorithm. So the main efficiency criteria are space. This means how much memory algorithm needs to complete, and time, how many time it will need to get correct result. Leaving the space on a side, I will try to discuss the problem of the time problem. And probably you think that taking much more powerful computer than mine will increase decrease the time needed to find the high component of a Fibonacci series. And it's true, but let's start to talk about computer speed. For many years, and there was in 1965 formulated some observation, which was called next Moore's law, telling that every about 2 years, number of transistors which can be put on a chip doubles. And when the number of transistors rise, the computer speed also rise. And here is graphing showing the number of transistors on a microchip, and as you can see, this rises almost linearly, but look, here is logarithmic x. So this rise in exponential way. Well, so far so good. Look at these. These are data taken for 35 years, starting from 60s up to 2010, with some predictions for the next year. And here are the same data gathered up to previous year. As you can see, number of transistors rise in linear way. The line isn't perfect, sorry, but performance doesn't, because we cannot, as you can hear, the frequency of each chip also rise linearly, but from some point, the frequency doesn't rise anymore, is constant. So the performance is almost constant. They do some improvements, but, well, there are some problems. Here, these brown triangles show power consumption in watts. And this, well, have to stop at some point, think about our mobile device, and think about heat production by microprocessor. So how to obtain higher performance of computers? Adding logical cores, adding processors. And these start somewhere in here. It was probably 2005. The number of cores that rise almost linearly, allowing for increase of performance of computers. But you know, there's another problem. Here, this blue line shows processor performance, which somehow is connected with Moore's law. But this red line shows the rise of battery capacities. As you can see, well, the rose somehow fast. This is once again semi-logarithmic plot, but rises much slower than processor performance. This is the main today's main problem. We have really powerful phones and have to charge batteries every day or every day and a half or something like this. This is the main obstacle in increasing the speed of computers. Of course, the speed of our computers is good enough for quite a lot of computations. But let's think about very simple problem. Finding the shortest route for a traveler who wishes to visit each of 200 cities. As for now, there is no computer that can find the road in fewer than millions of years of computing time. If the number of cities is smaller, it's really much easier to find the shortest among all roads, shortest one. Exactly the same with problem of factoring big numbers. Factoring means finding all prime numbers that divide integer. Well, but what does it mean big integer? 300 digits or something like this. And the good information is that all modern ciphering methods are based of some algorithm which to break ciphering the cipher information which needs to find factors of a really big number. Big means 2038, for example, binary digits. 300 decimal digits means more than 1,000 binary digits. How we can improve the speed of computation? Let's think about a very simple situation. After the final test, teacher got well, some grades, student grades, 10, 20, 50, 15, 33, or something like this. And think that it will be very nice to get these results normalized to 100. The biggest result will be exactly 100 and other will be changed proportionally. As you know, it's quite easy task. You have to find the biggest value in here. This is 50. And next you have to divide each value. And in this case, we got 1 and multiply this result by 100. It's quite easy job. The algorithm looks like in here. The variable I changes from 1 to n, and for each value we have to make very simple operation. But look, when the algorithm is written that way, this means that this operation, dividing 100 by maximum value, doesn't change in a loop. So it's much better to compute this factor once, like in here, and next, use this value for multiplying all other grades. And to be honest, every compiler finds for such things and removes factors which do not change inside of a loop. This is a loop. This is a loop repeating n times simple operation, finds things that doesn't change in a loop and computes it once, takes outside the loop and works that way. Well, the improvement isn't very big in this case, but well, I choose very simple example to show you how does it work. Another way of improving algorithms, this algorithm was, well, wasn't. So this for the first time presented here. We have list of elements, names and number phones, and we are searching for a phone number of a specified person. And having such names is quite easy. Here we have list of names. And starting from the first name, we are comparing. Each name with searched one is equal. If not, go to the next is equal. If no, go to the next. And at some point we can find the search person and algorithm ends. But in the worst case, when the search name isn't on our list, we have to go through all the list to tell that we cannot find the name. How to improve then this algorithm? Sometimes, as you know, the telephone books are sorted in alphabetic order. And let's assume that we have list of names, which is very long, 1 million. We're searching for a specified name, Y in this example. And this new, better algorithm doesn't go through all the names from the beginning to end, but here are names. The first comparison is made search name with the element in the middle of the list. And because list is ordered, here are names starting with A, here are names started with Z. So we are checking if the name is equal, but if not, we can get also additional information that search name is smaller or bigger, mean that in this situation, A is smaller than B, is smaller than C, and so on, is smaller than Z. So when we know that search name is smaller than name taken from the middle of the list, we know that we don't need to search to go through these names because the name is somewhere in here. At next step, we will also divide this smaller list into two parts and compare the name with this one. And next, find that the searched name is bigger than this one, so removing this part of a list. Now the list is 4 times shorter than the beginning. This allows for very big improvement. The algorithm is described in details on the slides, and here is its block diagram starting here. Compare y to the middle element of list found. Algorithm ends. That's the best situation, but when not found, we have to decide which part of the list will be taken for next step, removing the wrong name. And so on. As the list became empty, which means that we do not found the name, and algorithm ends this work. And here is an example with some fake names, and search name is Casey, and we are taking the name from the middle is Harrison. Casey is not equal to Harrison, is smaller than Harrison, so we can remove this part and focus on the first part. And once again, look here. In the middle of this list from Allen to Harrison is Davison. Casey is smaller than Davison, so we once again remove this part and take the name from the middle of this list is a Boyer here. Casey is bigger than Boyer, so we are removing these two names, and this is our list at that step. When we divide this list into two, we got Davis in the middle. Casey is smaller than Davis, smaller in lexicographical meaning of this word. So we are removing this name, dividing this into halves, and then the middle is exactly Casey. We can found it. Number of operations which have to be performed during this kind of a search depends on n, but not in linear way. In the first case, the simple algorithm, when the number of names, the length of a list doubles, the time in the worst case, of course, also doubles. But in, but in this case, it doesn't rise very fast. It's proportional to logarithm of n. So comparing the speed of algorithms is really a very difficult task, probably. If you remember the algorithm of normalizing students' grades, you can easily observe that the improved version of an algorithm is a little bit faster, but still, time needed to perform the algorithm in both cases, optimal and unoptimal, rises when the number of students rises. 2 times more students, 2 times longer time needed for completion of the algorithm. Of course, in each case, the second version of an algorithm, when the factor is removed from the loop, the time will be a little bit shorter. But talking about searching of a name, using this linear search, we have the same situation. When the list grows, the time needed to grow in the same way that that time grows. But this improved version the worst case situation time needed to tell that the name isn't on the list is proportional to the base 2 logarithm of the list length. So computer scientists decide to make such a really stupid notation, which is big O of n, telling that number of operations needed to solve the algorithm, to run the algorithm, or time need to run the algorithm is proportional to n. This binary search, the time, the worst case time of running this algorithm is proportional to logarithm base 2 of n. So when the list length doubles, execution time increases by 1, only by 1. This means only one comparison, one additional comparison. And after this comparison, we have number of elements divided by 2. This means exactly the same as previous. This table tells how much logarithm, 2 base logarithm of n is better than n. For billion list length of having a billion elements, we will need only 30 comparisons. And when the list has a billion of billions elements, we will only need 60 comparisons. It's very, very, very efficient algorithm, as you can see. When we have nested loop, this means something like here, we have to do something and we will repeat this in a loop. And this loop is also repeated once again in a loop. When we have to perform this inner loop n-1 times, this outer loop n-1 times, This means that we have to repeat this operation squared n minus doubled n plus 1 times. Because when n grows, squared n is much bigger than 2n, doubled n. So we can say that the time of this algorithm is proportional to squared n. Let's think about recursive version of finding minimum and maximum element of a list. This algorithm was presented on one of the previous lectures. And this recursive version works exactly the same as a binary search, but isn't as effective as binary search. In each step, we are dividing the list into two halves and searching for minimum and maximum value in each half. And well, we can try to compute how many times the compare operation will be done in this situation. When there's a simple calculation, C of n denotes the worst case number of comparisons required to recursively find minimum and maximum on a list of length n. And when the n is equal to 2, we have only one comparison. When the n is equal to 3, 3 comparisons. And when the, in general case, number of comparisons needed to find maximum and minimum in the list of length n is 2 times the number of comparisons done for half length list plus additional 2 comparisons to got the final result. So we can solve these equations getting something like this. Number of, when n is power of 2, even and power of 2, number of comparisons is exactly equal to 3 multiplied by n divided by 2 minus 2 comparisons. Well, you know, it's a little bit better than simple algorithm which will go through all elements and will need, in worst case, 2n comparisons. But this is still O, big O of n, because when the list grows, the number of comparisons grows linearly. Towers of Hanoi, also problem discussed of one of our previous lectures. Time to solve this puzzle is proportional to 2 in the power of n. Oh, exactly, it was if you remember correctly, it was exactly 2 in power of n minus 1, but when the n is really big, this 1 means nothing, so it's proportional to this. So when the problem size of the problem rises, the time rises very quickly. Well, we can start to think about non-recursive version of this Towers of Hanoi. And this algorithm looks something like this. We are putting pegs on a circle. First peg, second peg, third peg. And here we have, this is a look from up, 3 rings. The first move is taking this ring and putting in here. The second move, I will try to, whoa. Second move is taking the middle ring and make one evaluable move. This means go to this point, removing it from here. Well, this works better on a real whiteboard. The third move, this was the, well, okay, let's try to number these moves. Well, the first, the second, third move is once again using the smallest. Put it in here. The third move. The fourth move will be take the biggest ring and put it here. Once again, I have to erase this and this. Once again, it will be the fourth move. Once again, taking the smallest ring and put it in here. This will be the fifth move. The sixth move will be taking the middle ring and putting it in here. And the seventh move will be taking the smallest and putting it in here. Once again, we will need 7 moves. Is equal to in power of 3 minus 1. So we can make some kind of an assumption that this complexity, time needed to solve this algorithm doesn't depend on an algorithm use. This is a complexity of a problem, probably not of a found algorithm, but complexity of a problem. Another stupid problem is called monkey puzzle. Well, there's an anecdote telling that many years ago in the United States, when the children on the boat, on the plane board, so the children got such a puzzle with monkeys to have something to do during the flight. Alcohol is for older, but for children was such a simple problem, and what they have to do to put these squares in that order that each half of a monkey are the same on the lower and upper part, up to the according to the shape and according to the color. Well, when we start to think about this algorithm, let's assume that we cannot rotate the cards for simplicity, and the simplest solution is to number all these cards and next put it in order, like in here. These are cards, and check if the problem is solved. If no, we have to do permutations of the cards. Well, in case of 2 cards, this means 1, 2, 3, 1, 3, 2, 3, 1, 2, 3, 2, 1. And well, probably not all 2 on the beginning, 2, 3, 1, and 2, 1, 3. All 6 means factorial of 3 combinations. When we have 9 cards, we will have factorial of 9 combinations, and the simplest way is to use each of these combinations cards and look if this combination solve our problem. When we add rotations, there will be much more combinations, but let's stop at this. So time needed to solve this puzzle is proportional to factorial of n. So even in this case, when I discuss only few very simple algorithms, the complexity of the first one was time proportional to n. Complexity of second one was time proportional to base 2 logarithm of n. Another algorithm complexity compared to squared n. When we will have 3 nested loops, of course, the time will be proportional to n in power of 3. And other algorithms where the number of operations needed to solve it is much bigger is Towers of Hanoi. This one, 2 in power of n. Monkey puzzle, factorial of n, and also do exist algorithms which have complexity proportional to n in power of n. And look, when we have some linear complexity, even big problems can be easily solved. Because in this case, when the size is 1000, we have to perform 5000 operations. In this case, only less than 10,000 operations. This is a complexity of best sorting algorithm. 10,000 elements, squared n 1 million, and in power of 3, 1 billion, 10 digits, but still these numbers are, well, fit in our minds. But look, when we have complexity from the lower part of the table, even at the beginning, when the size is equal to 20, we got 1 million operations. It was here. When we have n equal to 16, there's a 19 digits number, 31 digits number, 302 digits number, when the size of the problem is so big. In this case, even worse, 19 digit number becomes earlier for smaller size. 27 digit number in this case is comparable with this one. So this table is divided by two, by this line. Numbers in here are bounded by some polynomial function. Maybe of order greater than 3 or something like this, but it's not very problematic. And numbers in here, the size, the time rises exponentially and even much faster than exponentially. Number of protons in the known universe is the number which has 79 digits. 79 digits. Look. Comparable with this. Comparable with this. Comparable with this. And number of nanoseconds since the Big Bang has 27 digits. Comparable with this. So think about this like each operation takes 1 nanosecond, and we start computing the problem, towers of Hanoi, of size 100. When the Big Bang has happened, and up to today, the problem wasn't solved. Very, very, very simple problem. To write a program who will solve this problem, you will need, well, half an hour probably, not more. So this polynomial, bounded by polynomial times of algorithm execution, is called reasonable time, and other times, exponential one, are called unreasonable time. Once again, the same table, but with rather than table, we have here a graph plot. Some here is number of nanoseconds in 1 day. So when each operation needs 1 nanosecond, we can solve during the day problem of size 500, which complexity is n in n squared 5, n in power of 5. But the same size problem when the complexity is n in power of 10, number of nanoseconds since Big Bang is unsolvable, practically unsolvable. When the time rises faster, and in power of n, we can solve during 1 day problem of size about 9 or 10 or something like this. But we cannot solve problems of size of 16. And once again, the monkey puzzle, let's assume that we have found the better than factorial n, worse than factorial n algorithm for solving the puzzle. And look, when we got an algorithm which will be, the time will be proportional to polynomial of the degree of 5, solving the puzzle of size of 300 elements will take 40 minutes. Not this is quite big number, but fits into time of a flight, yeah. But in case of complexity of this better than n factorial of n, 2 in power of n, puzzle of size of 60 will take 36 years, unreasonable long. But when we lower the number of puzzles, time is much smaller, 18 minutes versus 36 years when the size rises 1.5 times. In case of even more complex algorithms, even small problems will need a reasonable amount of time. Well, this is some kind of a discussion about classification of such a problems and names and these polynomial problems are called P problems. And these non-polynomial are called NP, non-polynomial problems. And when some problem is in class of P problems, this means that, well, probably we can solve it even if the size of a problem is quite big. In this case, we can exactly solve only very small tasks. But, well, you have noticed that all examples given during the lecture were some kind of puzzles, especially this difficult one. Towers of Hanoi or monkey puzzle. But this is the first notice. The second notice is that over the past years, the speed of computer rise, well, by a factor of more than 50. Probably we will find better algorithms. Probably we can tell the beginning, looking at the problem, that it will take reasonable time to solve it or unreasonable time to solve it, and we'll be happy with these problems which we can find reasonable time algorithms. But, well, look, this is another table showing how the time of execution changes when the speed of computer changes. When the number of operations needed to solve the problem is proportional to n, of course, when we got 1,000 faster computer, we can solve 1,000 bigger problem at the same time. But this isn't true for problem which number of operations is proportional to squared n. 1,000 faster computer means that the size of a problem solved by the same algorithm at the same time is only 30 times bigger, not 1000 bigger, 30 times bigger. But when we have Towers of Hanoi class problem, and now we can solve the problem of size C. When we got 100 times faster computer, we can solve the problem which size is bigger, rise only by 6. 1,000 times faster computer, the size of a problem rises by 10. This is really the problem. And unfortunately, the monkey puzzle problem is not alone. This problem of searching the shortest road between n cities is also of this class. And well, who needs to travel to visit 200 cities during his life, but think about the postman who have to visit several people having letter for them, and have to visit n places. And when the n is quite big, his road can be really long, and trying to find the shortest road can be very difficult. Well, no, probably no one postman try to solve this problem, simply goes through his block, and when can left letters during his working day, it's okay. If not, goes back and adds these letters to second day package. And of course, we cannot decide at the beginning, tell at the beginning if the problem has reasonable or unreasonable solutions. What we do with this parallel computing? Well, now each of your mobile phones has more than one core for computation, quantum computing, maybe. Do you have any questions? If no, let's try to start. Probably I don't finish it. Another slides about computer errors. Can the computer be wrong? This is really fundamental questions, because we are using computer on everyday basis. But I was talking during this lecture about different sources of errors. Measurement, this means absolute error. When we got some data which contains incorrect values, the results also will be burdened by some kind of an error. Well, sometimes when we know ranges of input data, we can try to predict the errors on the output results, but it's really very difficult and absolutely not easy. But well, okay. In most cases, we do believe in data, and we do believe in results given by a computer. But please remember that these results depend on the accuracy of data, so it's a really big problem. One source of an error. Another source of an error is humans. Well, the most common error is that human doesn't understand the application he or she uses and use it wrong way and got wrong results. Sometimes they are making errors in inputted data, simply typo, but not recognized at the beginning. At the end, you got wrong value. Sometimes people do not understand prompt asking by a computer and answer wrong way. But computer treats this data as a perfect and gives them results. Hardware. I was talking about today microprocessors, today computers that only used finite number of bits for storing data. So when data doesn't fit in this number of bits, it cannot be used. When the result overflows, the result contains more data, we will got wrong result that can more data that can needs more bits that can be stored in one word. The result will be wrong. We are fighting with this increasing number of bits. We don't use for today 32-bit computers, start to use 46-bit processors. But, well, please do remember, when we are using 32-bit arithmetic, the biggest value which can be stored is about 2 billion. The smallest value is about minus 2 billion. Increasing the number of bits to 63 gives us, well, some kind of a freedom, because I cannot name this number. Is really quite big, but please remember, it's bounded. This value is bounded between -9 something to +9 something, 9 quintillion to so on. Even if someone wants to name this value, but still it's bounded. And the results, when if you remember integer arithmetic, for simplicity, I use only 8-bit arithmetics. And here is the biggest value which can be stored using 8-bit. It's 127. 7 ones. And here's a sign bit. 0 means plus 127. When I add 1 to this, 1 plus 1 means 0. 1 goes here, plus 1, 0, and so on, so on. We got as a result such a value. This is This is signed byte, and this value was positive. This one is negative and is equal to minus 128. This operation, from arithmetic point of view, is not correct. From computer point of view, is, well, maybe not correct but introduced by design. We decided to use only 8 bits. So computer cannot do more. So all integer computations are performed in so-called modular arithmetics. In case of 32 bits computers, they are performed modulo 2 in power 32 and modulo 8 to in power 8 when in case of 8-bit computers. This means that we got only n last significant bits from the result when the n is equal 8, 16, 32, 64, number of bits of a result increases, but not very fast. In case of floating point arithmetics, the ranges in 32-bit arithmetics, the numbers are quite small. 1 multiplied by 10 in power minus 38 to 3 multiplied by 10 in power plus 38. The range is not very big, but when we move to 64-bit arithmetics, the range increases. We got values in power of 308, so much bigger, but still bounded. Results greater this are treated as infinity on the one side, smaller than this, but not negative, will be treated as a 0. So, we know how computer is constructed inside, so it's a design principle which we should remember about this each time using the computer. So there are not computer errors because, well, there are some bounds in computer working, but not errors. They are constructed that way. Computers are so complicated that in general, when something goes wrong, computer stops working. And probably you know about Pareto error correction in memories and such things. Probably you know about errors on this. We have to live with this. You know about errors during data transmissions. When you download a big zip file, sometimes happens and you cannot it unzip, have to download it again. Such things happens, but there's a kind of a random error. We are fighting with this, adding control sums using retransmission, automatic retransmission, not distinguishable by but sometimes happens wrong things on the manufacturer side, and I would like to tell you shortly about one case of this, talking about Intel microprocessors and the family which was called x86. In 1978, Intel has introduced 16-bit processors, and the names of these generations were 8086, 8186, 8286. In 1985, they introduced 32-bit processors, and the names of these processors were 80 486, 486, and the next generation will have the name 8586, but Intel decided that they should rebrand the name and stop using these cryptic numbers. And this new processor, the name of the new processor was Pentium. So they start advertising the new, better, bigger, faster processor, Pentium or P5 in 1993. And Thomas Nicely, a mathematician who performs quite a long computations, you can find everything about him in the internet, works in computational number theory. This means that the main tool for solving problems was computer for him. Bought a new microprocessor in 1994. Earlier this year, Intel testers realized that the new microprocessor has a bug. Incorrectly computes result of only one mathematical operation. They do nothing with this, thinking that the problem isn't really very big. The problem looks like this, that you got two numbers. Instead of get this result, 1.3302 and so on, they got, 1.33, and at the fourth place here was 7 instead 8. Nicely, which every time when he bought new computer, use new compiler, write new version of his program, start with some set of test data and compute this test data and compare results. If results are the same, computer was good, compiler was good, new version of an algorithm is also good. After buying a computer with Pentium microprocessor, he realized that some results differ, and it will take some time from July to November to search of a problem. He got confirmation that the bug is caused by a processor. This was confirmed by Intel engineers. So Nicely sent an email describing the error to some of his contacts, colleagues who work at similar problems. And after some times, this information spread over the internet and became known as the Pentium FDiff bug. Look, in the very beginning of November, he told to his colleague, but information go to the press, to traditional media, November the 7th. Intel acknowledged the book, but claimed that it was not serious and would not affect most users, and all processor cells at the moment don't have this bug. Yes, it has happened. And well, they decided to replace each faulty processor by error-free one. Well, situation was not very nice for the Intel, because value of shares goes down by 5%. Some competitors start to, well, notice that our processor is better than Intel, we have better processor and such things. Other situation connected with Intel processors happened many more than 20 years, almost 30 years later. There are so-called Meltdown and Spectre books. This is not connected with performing arithmetic operations. These books are connected with privacy and protection data from one application run on a processor protecting the data from one application to another application run on the processor. And Intel processor has a not nice bug, allowing in some situation to store some data. And this can be very important because when you browser using some kind of a modern browser web pages, process run in one page can store the data from the process run by other tab in the browser. You probably know that there are no those days are no simple HTML pages. Almost on each page there run some scripts, JavaScripts, and something. So in reality, your browser runs programs delivered by some external bodies to your computer, and well, there are some ways to solve this problem, but slowing down the computer operations. But in general, computers do not err. The main problem is with the software. Please remember, each piece of the software always will have errors. Try to lead so-called end user license agreement. This is taken from the Microsoft and you know, except with respect to the company warrants that software product will perform substantially in accordance with the accompanying written materials for a period of 90 days from the date of receipt, 90 days only. And any support services provided by companies shall be substantially as described in applicable written materials provided to you by company, and company supports engineers will make commercially reasonable efforts to solve any problem. Commercially reasonable. If it is not commercially reasonable, they will not. And with big letters, there is a such tutaj, this in this point. They guarantee money back up to the amount actually paid by you for the software product, or United States $5 only if you got the product for free and use it in your business, and because of errors something happened. Please do remember about this. Well, there is much more material on the slides, but it's time to end the lecture. Do you have any questions? So once again, please, 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 I will send a letter to you urging you to reserve terms and asking all reservants how many people will be involved in the presentation, and try to make some corrections. And please be prepared for the next lecture for 13th of January, next Thursday, to be ready for at least 4 presentation, maybe 5. Any questions?
Thank you, sir.
If no, thank you very much. Keep healthy.